Hello, everyone. Welcome back to the Microcontroller Application Technology course. Today, we will learn about the recognition of matrix keyboards. We will start by exploring three main aspects. Previously, we learned how to use two buttons to control the display of different characters on a single display. We also studied independent keyboard circuits. The advantage of independent keyboards is that they have simple circuits and are easy to program. However, each key requires a pin, and the resources of the microcontroller pins are precious. Therefore, independent keyboards are only suitable for situations with few keys or high operating speeds. What should we do when we need to use more keys? First, let's understand what a matrix keyboard is. A matrix keyboard, also known as a row-column keyboard. As shown in the figure, this is a structural diagram of a matrix keyboard circuit composed of 16 keys. We arrange these 16 keys into a 4x4 keyboard matrix, using some I/O lines to form the row structure and using other I/O lines to form the column structure. The intersection points of the rows and columns are not connected, serving as the key positions. By using this row-column structure, we only need X rows and Y columns to create a keyboard with X*Y keys. This significantly reduces the number of I/O pins used when connecting the keyboard to the microcontroller. How do we use this matrix keyboard? When using a matrix keyboard, identifying which key is pressed is generally divided into two steps. The first step is to quickly check the entire keyboard to determine if any key is pressed. If no key is pressed, the program moves to other functions. If a key is pressed, then the next step is taken, determining which key is pressed. Let's first look at the first step, determining if any key is pressed. We set the row lines as outputs and the column lines as inputs. Assuming we send a 0 to the 4 I/O pins of the microcontroller P1.4 to P1.7, making all 4 row lines low. When these 4 grounded row lines do not short any column line to ground, all 4 column lines are high at this time, and the data input to pins P1.0 to P1.3 is a 4-bit binary number 1111. If key K8 is pressed, the input signal will not be all 1. Because K8 shorts the second row line P1.6 pin to the 0th row column line P1.0, causing the P1.0 column line to short to ground, resulting in P1.0 being 0, while the other 3 column lines are not affected. At this moment, the data input to P1.0 to P1.3 is 0111. The program to determine if any key is pressed is shown below. The condition in the if statement, P1 equals 0x0f, is crucial for checking if any key is pressed, and debounce processing should still be considered in the program. Next, how do we identify the specific key that is pressed? There are two methods to recognize closed keys. One is called row-by-row scanning, and the other is called line reversal. Let's first look at row-by-row scanning. Row-by-row scanning is a common method for identifying closed keys, requiring the row lines to be outputs, the column lines to be inputs, and pull-up resistors on the column lines. Line reversal is faster than row-by-row scanning but requires both row and column lines to function as both inputs and outputs, with pull-up resistors on both lines. Using the example of key K8 being pressed, in row-by-row scanning, each row is set to 0 to read input signals. Firstly, scan the 0th row, meaning the microcontroller outputs 0xEF to the P1 port, the 0th row is 0, and the remaining 3 rows are 1, then read the column signals and determine if they are all 1. If they are all 1, it indicates that no key is pressed in the 0th row. Next, scan the first row, the microcontroller outputs 0xDF to the P1 port, the first row is 0, and the remaining 3 rows are 1, then read the column signals, and again check if they are all 1, if they are still all 1, then no key is pressed in the first row as well. Scan the second row. The microcontroller outputs 0xbf to the P1 port, the second row is 0, and the remaining 3 rows are 1, then read the column signals, which are now 1110, confirming that the closed key is in the second row, 0th column. This is the working principle of row-by-row scanning. Try to analyze by yourself how the process of row-by-row scanning would be if the pressed key is K2. The program to recognize closed keys using row-by-row scanning is provided in the diagram. The delay function is omitted in the diagram, so please add it accordingly. Because each row has 4 keys, when writing the program, the readability decreases when using more than 3 branches with if statements. Here, we use a switch statement to handle multiple branch selections. Its syntax format is as follows. During operation, the value behind switch will be used as a condition, compared with the values of the constants behind each case. If they are equal, the subsequent statements will be executed, followed by the break statement to exit the switch statement. If there is no value matching the condition behind the case, the statements following default will be executed. If no action is required when no condition is met, the default statement can be omitted. Through today's lesson, you should understand the structure of a matrix keyboard circuit, how to identify closed keys in a matrix keyboard circuit, and the usage of the switch statement. Finally, please reflect on today's class and complete the following exercises to reinforce the knowledge learned today, further deepening your understanding. That concludes this lesson. See you in the next class.